Hi, so I went over example 1 and 2 using Excel on a separate video, but now I'm back to finish the other examples. Example 1 and 2 will help you on homework number 1 through 4, but since we did them already, let's start with example 3 on page 3. So let me read the definition of exponential functions and something called a continuous growth that we have right here. So let's see. A function with an equation of the form y equals a times b raised to the x power. So in the first two examples that we went over, we had q equals q naught times 1 plus rate raised to the t power. And that's an exponential function. I meant to put q naught, where this q naught was the initial value, and we had the rate given, but this is the standard form, y equals a times b raised to the x power. You notice that the one that we used is very similar to that, just with different symbols. But this is called an exponential function. The constant a is called the initial value, and a is the number that we're multiplying, right? And in our case, on example 1 and 2, that was simply q naught. That's the initial value. And the positive constant b is called growth or decay factor. So in our example, our growth factor was, in our example of, I think, population growth, the growth factor, and I call it growth factor, not the decay factor, because for increasing population, it's going to be the growth. It is 1 plus r, okay? And if it's 1 minus, I think example 2 was a decreasing function, right? So if you look at example 2, we wrote the equation as q equals 485,000 times 1 minus 0.0125, and we raised that to the tth power, right? So here, the initial value was this 485,000, and the growth factor, I'm sorry, not the growth factor. Why shouldn't we call this growth factor? But we should call this decay factor, because this is home prices going down. We are subtracting. The decay factor is going to be 1 minus 0.0125. Okay? Alrighty. So we used those before, but now I'm kind of giving you the definition here. Compound interest is a standard example of an exponential function in which the equation is written using p for principal. P naught is its initial value, r for the growth and decay rate, and 1 plus r for the growth and decay factor, and t for time. Now remember this, you worked with this in 6.1, the compound interest formula. But we're gonna go ahead and remember I said for compounding interest formulas that are other than annual compounding, like if we had monthly compounding, then we use what? N equals 12. For quarterly compounding, we use N equals 4, right? N equals 12 for monthly, N equals 4 for quarterly. And if it was daily, remember we use 365 for N, right? And when N is 1, that's when that big compound interest formula turns into just that. But what if, because in nature, things don't always happen every day or at the end of the day or every quarter. It just happens all the time, like say bacteria growth, or if you want our money in our bank account, like investment. The quantities in nature change continuously, not just once or 12 times a year. Thus, scientists prefer to use the following representation of the equation. And we're not really going to derive this formula. We're going to just use it. We're going to be given y equals a times, a is still the initial value, and we're going to multiply that by e to the k times x power. Everything will be replaced by a number, but this e is already a number. Now, if you wonder what is e is not just a symbol. Now, if I ask you guys, what is pi? You know that pi is approximately what? 3.14 right? E is just another irrational number, very special, so we gave it a name. E. I typed up what E is a little bit. 2.1782182. So it's an irrational number, but it is a number. So if you type in E in your calculator, they're gonna give you that number. So E is going to be used for continuous growth or continuous decay functions. And you're just going to have to look for the keywords. If they say continuous growth or continuous decay, then we're going to pull out this formula and use it, okay? Now, this is just a box of everything that we're going to use, but let's actually use them on our example. Now, back to what E is. What is E? The number E is one of the most important numbers in mathematics. The first few digits are, I just kind of go up to like this much, 2.7182, well, I can go on for 2.7172 and more. It's often called Euler's number after Leonard Euler, pronounced Euler. I thought it was Euler, but Euler. Okay, so I gotta give you this important box because the ones that we're gonna go over are looking a little bit confusing, but you just gotta remember that these are our toolbox that we're gonna come back to. We're going to have to use these two equations to kind of find what they want here. So let me write down what K is. K is going to be the continuous growth rate. So K equals the continuous growth rate. Okay? Or decay rate if it's less than 0. Okay, so the first equation is relating e to the k power is equal to 1 plus r. So we'll use that first equation to go from the continuous rate to the regular rate, maybe annual rate or monthly rate, probably most likely annual rate. And the factors are going to be either 1 plus r or we can rewrite that as r is going to be factor minus 1. But I'm just kind of giving it to you right now, but it's not making sense right now, but we will come back and use these, okay? So let's use that on example 3. They're going to give you an exponential equation, y equals, let me see what they're saying, 250 times e to the 0.0945. Oh, can you go ahead and do me a favor and add x next to it? I'm missing x next to it. So please add x. I was missing the input variable. I better have x in there. But now, this is a continuous growth function, right? This is a continuous growth function because they gave e as the base of this exponential form. They want you to complete part A and B below. They want you to represent this e to the 0.0945 as a decimal to 4 decimal places. We're just going to type this in our calculator. That's what we're going to do for the first one. Give me 1 second. I'm about to open up my scientific calculator and type that in our calculator together. Now, you and I have the same calculator. Oh, well, I don't have that app on my pad. But you should be able to find the E button on your TI-30. But I'm going to go ahead and use this one, just an app that I downloaded. All right, so what we want to type in is e raised to the 0.0945. I'm going to hit enter. The number should be 1.099109. So let me go back and write that down. They just ask you to evaluate what this is. E raised to the 0.0945. That's going to be approximately 1.0991. They wanted 4 decimal places, so I'm going to write that much. All right, rewrite the equation in the form. Now, this is going to be a little more challenging, but it's okay. We know how to do this. Notice the first equation that we kind of boxed. Take a look at this. E to the k power is equal to 1 plus r, right? E to the k power is 1 plus r. We do know what e to the k power is. This is e to the k power we just found. That is e to the k power. So if you want to find the rate, all you need to do is, well, I'll set it up. If e to the k power is equal to 1 plus r, and we know that e to the k power is 1.0991, copy down the rest of the equation the same. How do you solve for r? What do you do to both sides? Yes, you're right. You simply subtract 1 from both sides. What we get is that the rate is going to be 0.0991. Now, we got the rate, and I needed to find the rate if I want to transform this exponential equation into a slightly different form. So let's write it. P equals, now, what is P naught? Can you tell me what the initial value is? We know that it is 250, right? So P naught is 250 times 1 plus r. I need to find the r. We just found it over here. R is 0.0991, and we're going to raise that to the x power. So that's how you transform it. You first find e to the k first. You simply subtract 1 from that value, and that is going to be your r value. So we use the first highlighted equation there to go from a continuous exponential growth equation to just an not a continuous. I guess I don't know what the unit is, but that's what we did. You can, I think you may be able to just add these together. I can. 250 times. The base is going to be 1.0991 raised to the x power. But that's what we will do, and let's try one more because this one was a little bit challenging, okay? All right, another one, and this is important, so I copied it down one more time. We're gonna use this one more time, okay? Given the exponential equation, y equals, again, look at me, forgetting the x again next to it. I'm sorry. Please write down the x next to the exponent. Okay, given the exponential equation, y equals 650 times e raised to the negative 0.0515x. Notice that k is negative here, right? That means this is going to be an exponential decay function. Complete parts A through B below. They want you to first represent e raised to the... I'm sorry, I got so many typos on this note. E raised to the, not that one. You see where that came from? That's from example 1. It looks like, I wanted to do another example with you, but just never came back and changed this number. Let's find this number first. E raised to the negative 0.0515. What I'm doing is I'm taking a picture of this before I go to the calculator. Now, I've been using that big calculator, but will it work on a small calculator too? And now, what we can probably do is, because I know there are calculators available there, I will say, I was Googling Dollar General. I'm going to Google search scientific calculator. Not Dollar General, scientific calculator. And you notice even though the most basic one, oh, you know what? I love this most. Maybe they have a good, this is awesome. Let's use their scientific calculator here. I'm going to do e raised to the, not square, but what was our exponent? E raised to the negative 0.0515. And I hit enter. Oh, oopsie, I forgot something. 0.0515. Hit enter. So I got the answer to be 0.9465. I'm gonna have to round that up. So let's go back and write that down. That is approximately 0.9465. They wanted you to do the round to the 4 decimal places, so that's good. Now we're gonna rewrite this in the other form. We do need to find what P naught is, the initial value. What's the initial value here? 650. Now, finding the rate is the harder part, but we got that equation, e to the k power. E to the k power is 1 plus the rate. So what we can say is the left side is 0.9465, and that equals 1 plus the rate. Okay? Subtract 1 from both sides. And you'll say, uh-oh, because if you subtract, let me do that on my calculator. If I subtract 0.9465 minus 1, I will get a negative number. And is that okay? Yes, that's okay, because this one is an exponential decay. Negative 0.0535 is the decay rate. Is the rate. So let's go ahead and write the equation. P equals the initial value of 650, right? Times, we're going to do 1 plus R. But notice if you're adding a negative number, that's going to turn into 1 minus 0.0535. And we're raising that to the x power. Let's simplify this. 650 times. Now, what's that number going to give us? If you subtract 1 minus, I'm going to see that number again. 1 minus 0.0535 is going to be, back to that 9465 number, 0.9465 to the x power. That 1 minus the rate, well, we just really, you see that's the same number as that right there, but oh, did that work too above here? Yeah, it actually did. Yeah, oh, cool. So, well, I always find the rate first. I always just find the rate and rewrite it and simplify it, but I think we just figured out that this is always gonna be the same as that number, huh? But you try it, you work on your homework, and if it works all the time, then we'll say, hooray, we found the rule. All right, now example 5 and example 6 and another one. I just thought this one was the difficult lesson, so I just got more and more examples ready for you. But whenever you feel like, oh, I think I got this, I want to try the problems on my own, feel free to stop the video and you can do that. Let's go over a couple more together. Population can be modeled by the exponential. Y equals, or doesn't say y equals 270,000 times e raised to the negative 0.0757t. Now, that's a negative number, so this population is going down. Where t is the year since 2019 and y refers to the population. We want to round to 2 decimal places as needed. The first one, they're saying, what is the continuous decay rate per year? Oh, remember, the continuous decay or growth rate. What variable did we use? Is the k. Continuous growth or decay rate is the k. And k is simply the exponent of the e term, right? So let's write that down. The continuous decay rate is this number right here, k equals negative 0.0757. So if I'm trying to fill in this blank, the population is decreasing. They use the word decreasing, so I'm not going to use a negative here. Decreasing at a continuous rate of, they wanted you to convert it into a percent. So I'm going to multiply that by 100. So I will get 7.57% per year. That's the continuous decay rate. Now, they ask you something very similar, though. Now, they're asking you, what is the annual decay rate? And this one, they don't want the continuous rate. So what we're going to have to use is that one formula we remember. E to the k power is equal to 1 plus r. Okay, that formula is so useful today. So what you're going to have to do is evaluate e raised to the negative 0.0757 and set that equal to 1 plus r. Because they're asking you for r in this case. So r is going to be e to the negative 0.0757 minus 1, right? Let's type that in our calculator together. All right, guys. I'm taking a picture of this. Alrighty, going back to my Desmos calculator that I just found on Google, I will do e raised to the, just going to type in e raised to the negative 0.0757 minus 1. I forgot the decimal again. 0.0757 minus 1. If I do that, I get that rate R comes out to be negative 0.0729. So let's go and write that down on our paper. R comes out to be negative 0.0729. And we want to convert this into a percent. So I'm just going to multiply this by 100. The population is decreasing. So that takes care of my negative sign. At an annual rate of what? 7.29% per year. They're so slightly different. They're slightly different. Because they're asking for two different rates. The first one is the continuous rate. The second one is the annual rate. Alrighty. Rewrite the equation in the form P equals P naught times 1 plus R to the teeth power. Well, that's going to be P equals, what's P naught? The initial population is still 270,000, and we're going to multiply that by 1 minus 0.0729, and that's getting raised to the teeth power. So P equals, if I simplify all the way, 270,000 times, now what's that going to give me? I'm going to go ahead and type this in my calculator. 1 minus 0.0729 is 0.9271. 0.9271 raised to the teeth power. So we got it. So our practice problems are all about converting a continuous growth or decay equation down to an annual growth or decay equation. In this case, was a decay, right? All right, how many people will there be there? Will there be after 8 years? Okay, I'm going to plug in my 8 equals, t equals 8 in the equation that I just wrote. 0.9271, and let's raise that to the what power? 8th power. And they said round to the nearest whole number as needed. So we'll do that. All right, hold on. Give me a moment to take a picture so that I can go out to my calculator. All right, let's type this in. 270,000 times 0.9271, close parenthesis, and we're gonna raise this to 8th power. I think I hit the button, but I don't think I did. I never type these decimal points. 0.9271 to the 8th power. Okay, so we got the population. So how many people are we going to have in 8 years? 147,350. Let's round that up to 59 people. Okay, so let's write that down. 147,359 people. All right. Now, really, example 6 and 7 are very, very similar. I just thought, this lesson is so challenging. I want to do more example with you. But you've seen enough. You've seen how to do them. So if you want to stop the video and try the homework, please do that. In fact, I will stop this recording and I will come back and go over 6 and 7 on a separate video for those of you who will need it. But